Welcome everyone. My name is Jim Lewis. I'm with SynthWorks. I'm the OSVVM Chief Architect. I'm also the current 1076 VHDL Working Group Chair, but hopefully I get to pass that baton off sometime soon. So, because that's just an administrator job. I like doing the technical work. Okay, so we're going to start out with the whys and whats of VHDL and OSVVM. All right, and then we're going to talk very, very briefly about the OSVVM verification framework, and then we're going to do a walkthrough of this faster than light approach that OSVVM has, and then we'll talk about extending it to a non-blocking verification component. But that's just going to be a sketch. First up, why VHDL? Well, if we look at the Wilson Research 2022 Functional Verification Survey, VHDL is #1 for FPGA design and verification worldwide. Now, some Europeans think, oh, well, that's because of Europe. No, Europe is balanced by Asia. Asia is Verilog. So I think this number reflects US. And what you can see here is VHDL is increasing. We had a little dip in the middle years. This is 2014, I think, yeah. And Verilog's not. System Verilog is flat. Okay, Verilog's decreasing. So FPGA, I think we're doing really well. We've got to get the word out to the FPGA vendors that it's time to think about not system Verilog verification components, but VHDL ones. Okay, so why OSVVM? Well, again, back to the same survey, OSVVM is the #1 VHDL solution out there. 28% of the market uses OSVVM. That's, if we refactor that into just the VHDL community, that's about half of the VHDL community using OSVVM. All right, so what is it? Well, it's a lot of things. It's a verification framework that allows us to do the little teeny unit tests as well as the full chip tests. All right, it's a verification utility library that provides solutions for constrained random functional coverage, error tracking and message filtering and scoreboards, basically bringing VHDL up to a full verification language, okay? Giving us the same sort of capabilities that other verification languages have. It's a verification component library that has an expanding set of verification components. It's a script library that allows us to do tool-independent scripting. Okay, so it's Tickle. It's an API layer that sits on top of Tickle. So you can write Tickle and OSVVM scripts, but you've got to run our API layer first. Okay, but then it runs on all the tools except for Xilinx XN. All right, and hopefully that's, from what I'm hearing, good news out of the Xilinx community, by the way, and hopefully that's coming. So co-simulation, we can run software on top of our hardware in the simulator at this point. So that means you can run your embedded software. That means you can run, write tests in C++. Okay. And because we also, two of the tools that we run on, GHDL and NVC are free open source. Okay, and they run with the same scripts you'd run Riviera Pro or ModelSim with. Okay, so if you want your software guys to start early, it might not be fast, but you can run a bazillion of them, right? Because they're free. We also have a test reporting capability that generates HTML, test suite, test case, and log files. And then if you run the CI tools, it runs JUnit XML file, or it generates JUnit XML files also. But the HTML ones are better, okay, because there's more VHDL specific stuff in there. JUnit was from Java, and it's just looking for a small subset test name and time, that kind of thing. OSVVM is free open source. Then it's developed by the same experts who helped with the VHDL standards. Okay. Yes, exactly. Okay. It has a long history. We started in SynthWorks classes. We've been at this since '97. The framework is since '97. We solved the problem. The way you solve the interconnect problem is different from then and now, just slightly. Okay. And then we have slowly added to it. So when people refer to OSVVM as the coverage and randomization, that's not just it. It's the full suite of things that we have. And actually, COVID was quite good to OSVVM because I traveled for training and I wasn't traveling anymore. So it's home developing. So it was very good for OSVVM. All right, so in this presentation, I'm going to look at this DPRAM. It's basically like the VRAMs in your FPGAs. All right, and it's got two address bus type interfaces. So we're going to have a DPRAM verification component that supports a single interface. And then our test bench will instance two of them. Okay, so as a framework, we look pretty similar to System Avalon, okay, or any other framework out there. We have verification components that implement the interface signaling. We have a test sequencer, which is where we put our test cases. Okay. And inside the test sequencer, it has architectures. And we use multiple independent architectures. I typically use configurations to bind everything up, but you don't have to. You can just use the last compiled architecture is the one that gets picked. Our goal is to make the DUT feel like it's plugged into the board. So make the verification components as high as fidelity as we can. Okay. At the interface level, we could care less about the internals. All right. Okay, so the framework, it's just structural code. It's just like what you do in RTL, so it's simple stuff, right? We have an instance of the DUT. We have an instance of the verification components. We have an instance of the sequencer. So there's none of this complicated OO stuff that the System Verilog community subjects their people to. Okay, it's stuff that any VHDL engineer can do, whether you design or verification. All right, and then when we build out the test sequencer, the ports are just transaction interfaces, which in our case is records. Okay, I'm pretty explicit on my name, so you see rec type. I think we grew up in a generation that learned to type, or already knew how to type before you even got an engineering school for many. Okay. All right, aspects of our test sequencer then. This is a little bit different test sequencer than the one we're looking at here. So, the whole test is in the file. Okay, so it's not like System Verilog where you're putting constraints out somewhere. You're putting the constraints generally in here, or at least some of them. We have a control process that's in charge of initialization and finalization of the test, meaning generate the reports when it's done. That's where it happens at. All right. We have one independent process per interface. So it's concurrent, just like your design. Now, that said, this is the way I like doing things. We can do a single process and drive it from a single process. So, I just think that leads to insanity. Okay. Because you have things like read that need to return data, and that's got to be blocking. All right. So our tests then, we just construct them by calling transactions. Okay. So we're going to create this transaction API, and that's how we're going to build our tests. And it's easy to do directed tests. It's easy to do constrained random tests. It's easy to do scoreboards and functional coverage in here. Now, they are independently running processes, and sometimes we need to synchronize them. Okay. Here, I'm going to show you two synchronization points that are very test specific. We wanted the AxiStream manager setting up the DUT so that we can talk to it. We don't want to start talking to it until it's done. So we use this wait for barrier with test init, and a barrier in software anyway is stop here until everybody that's hitting the barrier has hit the barrier, and then everybody continues. Okay, so that's what's happening here. So it's actually the TX process is getting there first, the AxiStream manager is getting there second, and then they both release once the AxiStream manager gets there. All right, and we also do it for test done. Okay, so the control process hits it right away. The control process adds another parameter. It's a timeout. The test done, wake up at 5 milliseconds. Well, that ends up being a watchdog timer, right? So if your test died, yeah, we don't want to wait forever. And we don't want the whole nights of regression runs to stop just because the first test failed, right? Yeah. Anyway, as we're running, we're doing self-checking. And we're recording against OSVVM's alert log data structure. So that when we finish, we call this end of test reports. And there's a whole flurry of YAML files that get written out. Nothing for you to worry about, but the scripts take those YAML files and assemble them in HTML. Okay. So the standard reporting in especially the XUnit files or the JUnit files, they want like your test time to be reported at the beginning. Well, you've got to have a data structure, and you've got to have written it out separately so that you can write it out and then collect it later. Okay, steps then. How do we develop verification? So now we're going specifically down into the whole of what is it, how do we do these verification component things? So step one, we've got to build out a transaction interface, and that's these controller recs here. Step two, we got to build out the API, writes and reads, or sends and gets, that sort of thing. Okay. And step three is write the behavior verification component. Okay. And it's all this is tedious to do, but it's not hard. The interface for us is just a record. Now you might be saying, wait a minute, you're using it as an in-out. We all know there's drivers issues with that, right? So we've solved the driver issue by having types with resolution functions. And the resolution functions in resolution package, as part of OSVVM, use maximum based resolution, hence the suffix max. So they just pick the biggest number and they ignore if there's multiple drivers. But generally, we do catch that. I'll show you that in a few minutes. Our long-term plan is to migrate to VHDL 2019 interfaces, okay, which was designed exactly for doing things like this. Okay. So, and it's a very simple step. It's a mode view declaration that needs to be added. I've kind of tested it out, making sure that the feature works the way we wanted it to. Just not enough vendors do it, so we're not going to put it a permanent part of the library just yet. Okay, step two, we need to build our transaction API. And that is just create a bunch of procedures that do the things you want done. So I have read transactions on the interface, and all I need to do is I need to take the things from this command and a command name and populate the record with that. And then I call request transaction. That says to the verification component, hey, got something for you. Put stuff in the record. I'm ready for you to do something. Okay, that's all it does. It's pretty simple. And then it blocks, it waits until the other process in the verification component runs and does its thing. And when it finishes, this returns and we get data. Okay, so this side is fairly simple, fairly tedious. We'll come back to that though. Okay, so our verification components, we have the DUT interface, we have the transaction interface. For me, the transaction interface is always the record type. This could be a record or not, just depending on how you feel about it. For the small interfaces, I've done it as individual signals. For AXI, there's an insane number of signals, and you don't always use them. It's much easier to throw it in a record and deal with it that way. So that's what we did there. You just have to know how to break a record out, right? Because you can, for every port that's a composite, you can map it signal by individual element by element, whether it's an array or a record. Okay, so wait for transaction is the companion to request transaction. So the verification component stops until something happens on the ready line, telling you to do something. Okay. All right. Then we look at the record. When we got something, something's in the record, so we got something, so we decode it, and we do something. Okay. Kind of hypothesizing that we're using subprograms. I don't. This is the point where I write code. Okay. And often things get much more complicated. Okay. So coding a verification component in OSVVM is well within any VHDL engineer's capability. Okay. All right, now some simplification. Made this observation, many interfaces do the same sorts of things. Okay. We have address buses or memory mapped interfaces, such as AXI4 and Avalon. They do reads and writes. Okay. We have streaming interfaces, AxiStream or UART. They do sends and gets. Doesn't matter how wide the interface is, they're doing the same operations on the interface. All right. For these interfaces, OSVVM's model-independent transaction library defines the transaction interface, the record, and the transaction API, the procedures. So what we're trying to do then is build a interface that's a superset of what you need. So if you run into something that's not in there, you report it as a bug or as an issue, and we come back and collaborate and figure out to add it is the whole, yeah. So we have the record defined in there, and then we have the procedures. This is just a very, very small snippet. Okay, so write, read, but also things like verse, write verse and read verse and all that kind of stuff. We do the same thing for the stream interface. All right. So our record, our sends, and our gets, our send verse, get verse. All right. All right, so benefits. Well, we accelerate a number of things, and the most exciting one is the last one. The VC development, the test writing, the documentation. Okay, we'll come back to that. Verification component developers get to reuse the model independent transaction library. So they get to skip defining the interface, skip defining the API, and just go right to writing the verification component. It makes it as easy as writing a procedure. Okay. Test writers, they already know the transaction interface. So if you worked with one address bus interface, it's the same as working with another one. Okay. And if they've written any macro sequences and procedures, they might be able to reuse them. Okay. Our co-simulation interface supports all model independent transaction-based verification components, including ones you write. Okay, so if you have some different bus interface you want to write, yeah, no problem. Documentation, the verification component only needs to identify which transactions you support. That's a table. That's not describing how they work, because instead we've got that described in the user guides. Okay. So it's just like referencing out your waveform diagrams. You don't need to reproduce all the waveform diagrams in your spec. Okay, so how do we get to faster than Lite then? So our approach is write a simple blocking verification component. Okay. This might not be enough to finish your project, but it's enough to get started. Okay, and then start writing functional design tests, because a blocking one's good enough for that. Okay, write basic interface tests. We may need to upgrade the verification component later to support more complex interface tests. Okay, things that independent activity on interface, like on Axi, right? You need something more complicated to do that. You can't stick with just a blocking component for that. So what do I mean? I should have got to here sooner. What do I mean by blocking versus non-blocking? A blocking API call is one that waits until the transaction completes. Okay, so can't do simultaneous things. So if you think of Axi, it can't do write and read on the same clock cycles. Okay, a non-blocking API call queues the transaction and returns immediately. Okay, and OSVVM model independent transactions support both. So we have use models for both. Non-blocking, again, is required when the interfaces support simultaneous activity. All right, benefits. We have one verification framework that runs all tests. If you start with subprograms with procedures and switch to verification components, you're supporting and maintaining two different verification hierarchies. Whereas this one framework runs everything. We start simple. We deliver an initial verification component sooner. Then if you have a whole team of people in the verification environment, people can start writing tests right away, start testing things. Okay, as somebody else goes out and upgrades the verification component, they have the full asynchronous capabilities. Okay, so how do we do it? Well, we're going to start identifying things. We got to start by identifying what are the transactions on the interface. Okay, and every interface is going to look a little bit different. And then we need to look up transactions in the model independent transaction reference manual. And then it's basically building it out. So package references and stuff, that's going to be building it out. All right, so if we look at the DPRAM, what is it doing? Well, it does a write cycle, a single cycle write. It's all clock, bam, it's in, it's done. Well, it finishes when it does internally, and we don't care. If from an interface perspective, we're done. Read operation can take 2 or 3 cycles, depending on how you have the VRAM, right? But it is a thing. It's either 2 or 3. It's not ever a mix of them. Okay, and then we can also read simultaneously with write. The read data comes back a clock cycle later, and it may be the data we wrote, It may be a data from that it was previously stored there, again, depending on how you had the VRAM configured. Okay, so the next step is to look up the transactions in the model independent transaction user guide. So for this interface, we need to support write, read. Read check's a nice one to have. That's part of our self-checking scheme. And then write and read to get that write and read simultaneous. Okay. So the next step then is we need to look up the operation in the user guide, because this is what you're going to be decoding in that case statement. Okay. These are the things we have to decode in the case statement. And this is actually a direct clip from the manual. Any directive transactions you want to implement. I always implement wait for clock. Wait for clock allows us to wait for time in our test bench, but it's time that correlates with what the verification component is actually doing. So you can wait for like 5 clocks or something like that. We can get the alert log IDs. That's an OSVVM thing for error reporting and handling. We can get the transaction count. So any of those that you want to support in there, supporting is trivial. Okay, because you can actually cut and paste some of these things from the OSVVM guides or OSVVM verification components themselves. All right. So step 1, we're going to create alert log IDs. And we could pre-process inputs. Just depends on the interface. If you have H's and L's coming in on your interface, I don't like my verification component to have to test for H and L's. So I just take care of them right at the beginning with like a 2x01. So that's what I mean by pre-processing. And then we have either a transaction handler or a transaction dispatcher. A handler, if it's interacting with the DUT. A dispatcher, if it's taking the command and spreading it out to a number of things like we do in the XML. Okay, and then we'd have corresponding, if we had a dispatcher, we'd have corresponding interface handlers. We might have protocol checkers, depending on how complicated your interface is, or even how simple it is, like a RAM interface. If it has separate write and read lines, you never want both of those asserted at the same time. And it's so simple to catch it in code. Where good luck on the board if it's a glitch. And then you might have timing checkers. If you have complicated timing checkers, I recommend you look at the Vital book. And there's, or the Vital timing library, and there's a great book on it by Rick Munden. If you need a reference, I can get it for you. And then log your results. Okay, so package references. One thing we need to reference is the OSVVM utility library, which is the one that was historically called OSVVM. And then we need to reference the model independent transaction library, which is OSVVM_common, and its context, OSVVM common context. Okay. And then our verification component, we already talked about the DUT interface and the transaction interface. The other thing I want is working with the alert log IDs. I like having an alert log ID, an error reporting level for each verification component. And I give 2 options to name it. One option is we're going to scrape the name off the instance path. So you do tick path name on an entity, you're going to get this long name. The very last thing in that name is the instance label. So if you're methodological about naming them, then you're going to come up with that. And I always name it component name _1 for the first one, component name _2 for the second one. So I've got a really good set of names. Alternately, you could set this generic, and then if that generic's longer than 0 in length, you use it. Okay. And if else is something in the OSVVM library. Okay. So creating the alert log IDs, again, the whole purpose is we want to associate messages, error counts, and controls with a particular verification component. By doing this, it allows you to turn off messaging from one verification component and turn it on for another. To understand the importance of that, imagine you have an info level message coming from a processor model that you're polling, and another one coming from a UART. Well, you're never going to see the UART messages because there's going to be so many of the processor ones because the UARTs are so slow. So you can turn off the info flags for the CPU, leave them on for the UART, and you get all the messages you need. Okay, that's the point. So to do these things, we use new ID to allocate something. Most OSVVM data structures, the alert log IDs, the coverage modeling, if you've seen it since 2021, summer of 2021, was that scoreboards are singleton data structures, and they all get created this way. We call new ID and it creates them. So if we were OO oriented, we'd say that's constructor, and it really is doing that, just like you do in OO. And then we create child IDs. So if we want to further break down our error reporting or something like that, we can if we want. You don't have to. I do suggest strongly that you use the names that I'm using, model ID, and like for the transaction rec, I always use transrec. If you like cutting and pasting from other designs, that facilitates it. Not a required practice, but just a good practice to do. And ID references storage in the singleton. So internal to it, at least, there's an integer that's referring to an index in an array that's inside the data structure. Is all it is. It's a lot of work, but it's pretty simple once you understand what's going on. Okay, and then to change the settings, we actually have two options to change the settings here. We can look up the ID by name. By knowing this name, we can look it up. By calling new ID again on that same name, it'll return you that same ID. Okay. Or we can look it up if we implement the get alert log ID transaction. Okay. And by naming it, when we put out messages, it tells us who did it. Okay, so it gives us a pretty good trace back on. Okay, sometimes we need to handle initializations on interface things. And that gets complicated because our process, historically, I was used to using the iterative nature of the process all the time. But I finally realized in a verification environment, I don't have to do that. That's just an RTL constraint. So in a verification environment, what I'll do is I'll initialize things. And then instead of using the looping nature of the process, I'll just use a loop without iteration scheme, is what the language calls it. So it's loop and loop. And then I write the rest of what you saw before inside of that. So let's get into those pieces then. The wait for a transaction, it finds a transaction, but it also makes sure when we start the code down here, make sure that we're aligned to clock. Because I like having delays on my stimulus, and I need a proper alignment to clock. One of the problems is, what if somebody does a wait for 10 times T period clock in a test bench? Okay. If they do that, then you need to realign the clock again. Okay. Or if you used one of the wait for barriers, now you need to realign the clock again. It's automatic. Okay. It's just checking some of the attributes to see am I at the same time step as the clock edge happened at. All right, so looking at one of the transactions, we're going to look at the read and read check transaction. We kind of bundle them together. Step one of a read cycle is put out the address. Make the control line say that it's a read. The right line is set to 0 to indicate read. And we hold that for clock. And then the next thing I like to do is destroy the address. Because on a broken dot, you might keep looking at address. And if the address doesn't stay valid, it dies. Okay, I've actually lived that. So we want to pull it away as soon as it's not supposed to be there anymore. That could be not the address. That could be X's. That could be random number. It's up to you to decide what the verification component really should be doing. And then we wait for data to be ready, either 1 clock for the data, or if there's that extra output register, 2 clocks. Generally, this would be a generic. And then we need to do the rest of the reporting stuff. So let's take a look at that. We're going to look at the reporting for a read operation first. Okay, so we said if it's a read check, read check is actually part of the model independent transaction library. So it allows us to classify the operations so that as we add to it, we don't have to go fix our models, right? Okay. So when we do a read check operation, we might want to conditionally print. And that's what logs are all about. Logs are all about conditional printing. No, we're using the ID, we're logging against the model ID, and they print when they're enabled. Okay. and they're disabled by default. The control is either from the global settings, or we can go specifically down to this ID if we want to. Okay. Logs have levels, just like alerts, asserts, and VHDL have levels. So the levels here are always info, debug, past, and final. Past and final are kind of special. Always is kind of special too. Always means always print it. Okay, so it's always enabled and always print it. Info and debug are really for turning things on and off. And we really haven't added any levels beyond that to it at this point. Thought about it. We see System Verilog having all these numeric levels. And I think it's really the reason why they have all these numeric levels is they're trying to figure out how to turn on specific verification components. And I don't think numbers do that. I think this more act does that.
No fail or warning type message levels in there. You can quite often get an error or a warning messaging log levels on different systems.
Are you getting it in OSVVM?
Yeah. I mean, you got all.
Oh. This is just for logging. Logging means life is good.
Oh, okay.
Logging means life is good. So we'll see those here somewhat. I'll get to it. I'll get to an alert in a minute. So if it's a read check operation, we also need a sense of logging, but we need a sense of pass fail. Okay. So, and affirm if. The affirmations are all set up to be part of our self-checking. One of the things that distinguishes this from our other things that do checking is that these count as a quality measure. Meaning, when you run a test, if you don't get any affirmations, you haven't done any self-checking. And we can check for that, and we could say, oh, not so good. Okay, it's a vacuous pass, for example. Okay. All right, we'll come back. Let's get synced up with this one. So what's this all about? Affirm if does checking on these two parameters. Okay, I think it handles a number of different types. So, and so if it passed, then it's going to print a pass message if the log passed is enabled, which it's not automatically. If it's an error, it's going to print out an error always. Okay, so and it's going to count it. And we'll come back to the alert with more details on it in a minute. So directive transactions such as wait for clock, they're pretty simple to implement. We didn't implement this in the test bench level because that meant we'd have to bring all those different verification component clocks into the sequencer, and then we could get them twisted and bring in the wrong one. And I don't want to do that. Okay, instead we're calling up the verification component and saying, hey, will you wait for one of your clocks, please? And it does it. Okay. So, and this is just a call into the OSVVM utility library. And then get the alert log ID. Well, we have it. We're just pulling it. And getting the transaction count. Funny thing, a lot of the handshaking, I used to do handshaking with standard logic vector, and then I went to bit for test benches because I realized I didn't have any need for X's. And then I went to integers. And I kind of fell in love with integers. And this is just one of the side effects of using an integer count is that the ready signal indicates how many transactions have completed to date, because I'm incrementing it every time we do a transaction. So we initialize it to, effectively they get initialized to 0. So, yeah. Okay, the alerts. So we also have a multiple driver detect because you do need that. So I said most of the things use a max resolution, which is cool and fine, it works well, except for the resolution that's on the operation field. And in that, it has a special resolution function. And if it sees two drivers, it just says, nope, I'm not going to pick either one. I'm going to pick this special one, multiple driver detect. All verification components should detect this because in our test benches, in our test sequencer, we often copy and paste and we forget to change a name. And we need this. This is an important thing to put in there. And really, if you have followed the pattern and used model ID and followed the pattern and used transref, just cut and paste. Just cut and paste. So alerts are all about signaling and counting errors. So asserts in VHDL signal errors but don't count them. Well, until 2019, we've added the OSVVM-like interface to it and required the vendors to count it. But that's going to be like a general count against language things. And once we get 2019 all implemented, the report alerts will pull that into. Okay. So control, again, is either global or just for this ID. And we have failure, error, and warning. So everything from assert, except for note. Note's not an assert. Note is more like a log. Okay. They're enabled by default, and they're almost never disabled. But the mistake of disabling them and not re-enabling them, our reports track disabled accounts. By default, we report disabled accounts as an error. So you have to do a two-step process to turn them off. If you successfully did that, and then you're reviewing the reports, you'll see that there's disabled alerts. So it's just a mistake that could get us in bad trouble. So I want to make sure that we're not. Okay. And by the way, when we get failures, it stops the simulator by default. You can change that. We got to change the stop counts, but it will stop the simulator. It's also a good practice to detect unused transactions. Okay. Models sometimes need to be configured for different settings. Like you want to set different signals outputs on the AXI interface, and you're not driving. They're not part of the transaction model because they couldn't be part of a general transaction model. So for setting the privilege level, for setting different things like that, we use set model options. Set model options is a general thing. So it takes the record, it takes an integer field, and then it works with an option value. And that option value can be integer, Boolean, or standard logic. Again, model options is an integer. Okay. Options are commonly directives, but they can also be transaction extensions. But if you do transaction extensions, file them as an issue against the library because we want to consider those for candidates for adding to it. It's a living library. If the setting is static, just use a generic. So like the output register, when you put the DP RAM down in the system, fix it. The verification component can only do that. Okay. And again, for the set model options, how do we work with it? We just look it up in the user. Okay. Okay, so, and what we can do with model options, if we're going to work with it directly, is set up constants. The old Kernighan and Ritchie C enumerations. Okay. And then we would define a corresponding signals for every one of these settings inside of our verification component. And then when we call set model options, we decode the operation field to find set model options. We decode the transactions field to figure out which options we were setting. And then we do our thing. I should note, I'm not really happy with working with integers as enumerations myself. So in the AxiStream and the Axi models, you'll see that we use enumerations, and then we use a abstraction layer on top of set model options. So we have a set of procedures that what they do is they translate the enumeration into an integer value, which is just tick pause, right? Type tick pause, yeah. So it's an easy thing to do. So we convert it to an integer so we can, I like enumerations because you can never accidentally use the same one number twice. So. All right. So everything we've done up to this point has had the transaction record as a port. Okay. But a port is a problem because if we want to put something like an AXI verification component in a Xilinx chip because we're scanning in for the Zinc processor, right? It can't have a port. Okay, so that's what our virtual transaction interfaces are all about. All right, so what we've done so far has been with record ports. And let's call that our connected transaction interface because we're connecting it up like RTL code. And OSVVM virtual transaction interface sneaks in. We're going to use VHDL 2008 external links. something I like, but I'm not real excited and not as excited as I could be about it because VHDL doesn't do, one of the free simulators doesn't do external names yet. Okay. There are workarounds for that. Okay, so what we do then is we create a signal. And after the ports end is a declarative region, an entity. And I like putting this there because then it kind of mirrors what the other one did, where we had a port up here called transrec. Now down here, we have a signal called transrec. And I kind of, the things I put here mostly are things that I want to access by external names. Okay, so this is one of them. I put this constant down here for another reason. I put it down here because this is the only difference between the connected interface and the virtual transaction interfaces. Okay, is how we construct that name. It's slightly different. Okay, and I just, when I make AxiStream full and AxiStream supports both the connected interface and the virtual transaction interfaces, I just copy the architectures between. Okay. All right, so what's different in the VTI test harness? Okay, we get rid of the signals. So we get rid of the signals here. Instance of the DUT doesn't change. Instance of the verification components, again, we got rid of the signals. All right, and then test control, we have choices here. We can map up the external names directly to this point, and this does work very well. Okay. So the external names connect to the test sequencing ports. That's one option. The other option is to delete them off of here and in test control itself, add aliases to the external names. And I make the aliases exactly match the ports that would have been on test control. Because by doing that, I can use the same test cases. I have a test harness for the connected transaction test bench, and there's a separate test harness for the virtual transaction interfaces, and we just run the same test architectures against both because we kept the names between the two different test harnesses. Everything's the same. Okay. The only thing that's different is which one we instanced. You might be wondering, why didn't I do that with the configuration? Okay, because sometimes you can. I don't think you can here because of the port differences. But even if you could, I don't want to do that because then for every test case, I'd have two configurations instead of just one. So sometimes these things I can do with configurations, I don't because I don't want that multiplying factor. Having two test harnesses is cheaper. I call that the configuration explosion problem. When you get too many parameters that you want to configure in a VHDL configuration, you end up with just a boatload of configurations. Yeah. Okay. Non-blocking verification. So a non-blocking API call, again, it queues the transaction, returns immediately. So this increases the complexity. So why on earth do we even want to do this? Well, let's go back to our DP RAM. Even the simple thing like a DP RAM needs this. Okay. If we look at our normal read, yeah, that makes sense. I don't need it there. Right. But, oh, wait a minute. How do I get two addresses out? Because this hasn't finished yet. Okay, so this is simultaneous activity on that end. So then to do these, we have to have a non-blocking dispatch. All right. So what are our transactions? Well, we have write asynchronous, read asynchronous, just puts that out and lets it go. So this one is with data. This one's just the address. The corresponding things here, and it's named after the system Verilog, similar kind of constructs, is try read and try read check data. Okay, and this has an available flag that comes back with it and says whether it was successful or not. And you can basically pull that and keep trying it. These two are blocking, but they don't have any meaning in a normal blocking transactions. They pair with this. All right, and then we have read and write asynchronous, and the read part of the asynchronous is just the address again. Okay, so let's take a look at why how do we do that transaction then with what we have? So read check, yeah, we can get that first transaction in. And when this finishes, we're going to be on the right-hand side of this. Okay. So to queue these up, we're right here at the left-hand side of where we're driving A2, and or the right-hand side of the read data. And then we call read asynchronous trace. And that puts those two read addresses out. They're queued. We have not moved in time. And then we can do our read check data. Okay, so this is the value of those asynchronous transactions. Okay. How do we architect it then? So we're not going to have time to get into it in details, but each independent aspect has to be a separate process, because that's how we get independent things. All right. So we have the transaction dispatcher, yeah. And so it's not handling things anymore. It's just handing off the address, write address or read address, and write data and type of operation. Okay. And then if it was a read address that came down, we indicate to the read handler that we're expecting data, and it'll grab data in the program. And then it'll present it back in a FIFO. And the FIFOs are coming, OSVVM scoreboards have a FIFO inside, and it can be used as a FIFO. And the only disadvantage to using it as a FIFO is that you have a lot more that you have to instance, right? You have all the generics that the scoreboards give to instance, but if you're using it as a scoreboard already, then there's no reason to have a separate FIFO. So, and we already have a scoreboard FIFO in the library for standard logic vector as well as integer. And the standard logic vector is unconstrained. AxiStream Manager. This was the one I worked on when I developed the asynchronous transactions. Because if you look at it on Axie, it's insane. So we have the, oops, nope, we don't. We have the transaction dispatcher, but then the write address and the write data are independent. And then the write response is independent. And then the read address and read data are independent. Okay. So we have to have an independent process for each of those, and FIFOs in between, all that. And it has to be, the Axie spec says a subordinate model must be able to accept data before address, because they assume that in the transfer network that data can get there. You know, normally we would never expect an AxiStream manager to dispatch the data before the address, but due to skews in the networking, it can end up there. So we have to test that, and we have to be able to test that. All right, so if you don't have OSVVM already, how do I get it? Well, you clone it from Git if you're a Git user. So, but make sure you're doing recursive, because we do use submodules. Okay, so that recursive is important. Or you can get a zip file from OSVVM. Okay. So if you hate Git, you don't have to like Git. Okay, so if you're using ModelSim, QuestaSim, or Riviera Pro, the startup's all the same. Okay, you start up the tool, and then let's say you start it in the same directory as OSVVM, as you put OSVVM libraries in. I like creating a sim directory to run the simulations out of. So this is Tickle for creating a sim directory. And then we change directory into it, and then you source the scripts. Once you've sourced the scripts, you can build the libraries. And you just say build. And if you have some complicated path, because you decided to put sim somewhere else, there's $1 OSVVM libraries. It's now defined. Otherwise, you could have just done // OSVVM libraries, and then OSVVM libraries.pro, and then run the test or run demo tests. Either one is fine. Okay. So each verification component has a run all test and a run demo test, as well as the top level has a run all test and run demo test. Oops. We've got a lot of documentation stuff out there. So our resources, HTML documentation, PDF documentation. PDF documentation comes with the release. So if you got the release, you have it. The prequel, in many ways, to this presentation is this one here. It's out on GitHub or on YouTube, excuse me. And then we have 2 on Aldec's website about our test reports and our verification data structures. Each of the presentations is a little over a year old now. Things have been, everything's been moving. So I'm hoping to get another recorded one of the general one soon. So we also do training. So, and we do training from First EDA. So yeah, talk to David or Adam, who was here earlier. So in UK and okay, so wrapping up then, an ordinary Lite approach tends to be very simple, but also less capable. Okay, and they do things like use procedures to drive the signals. So it's a different test architecture than what we'd eventually use once we go to verification components. OSVVM's faster and light approach, we write a simple blocking verification component. Okay, we write functional tests and basic interface tests. Later, we upgrade to non-blocking verification components for testing. Okay, the level of this is such that any VHDL person can write it. Okay. So we can get started quick. It's no more complicated than writing a procedure. Okay. So we simplify verification component development by providing the API and the interface in the library. So we just have to write verification component behavior. You can use behavioral, you can use RTL line coding. So people who are experienced at RTL, if they're just learning writing test stuff, it's okay. So it's okay to write more RTL-like thing. And don't get hung up on it, because I've seen some things in verification environments that work better as RTL-like things. And so it's as simple as writing a procedure, except we have a lot more capability and it can be written by any VHDL engineer. So that's one of my thoughts, is that it used to be when we started doing, when I was doing gate design when I was younger, people would start in the verification environment and they'd learn to design, and in the next project they could go on to design if that's what they thought their route is. And I think we should come back to that, because I think OSVVM makes verification at the transaction level easy enough that we can do that. We can have people start in the verification environment writing tests, maybe learn to write verification components, maybe not, maybe go on to an RTL design aspect. Okay. So with OSVVM, all you need is OSVVM. We have a complete solution. We have 5 minutes left if you guys want to ask any questions, or if you've already been using things, you can tell us how it's going.
Oh, just ask online if they have.
Yeah, if they have questions online, they can give me.
So on that double read, 2 consecutive reads, you've got 2 non-blocking things, but
Yeah.
the data is synchronized to the clock. How does that? Is there inherent synchronization within it, or do you actually have to put it in?
Let me get to the right slide and I can here.
There, yeah, you've got 2 read address ACs.
So that goes down to the handler, and the handler puts 1 out every clock.
Okay. So it's inferred.
And everything in the handler, everything in the transaction dispatcher is pretty solidly aligned to clock. I never recommend doing like wait for 5 nanoseconds.
No.
I look at, I've seen test benches like that and I'm like, amateur. Because I think everything you do, you want, for me, everything I do is aligned to clock, and then all data that the test bench drives has a propagation delay to it. That way you immediately know that if there's a signal that's doesn't have a propagation delay on it, it's an RTL signal. So you can even identify the source of things and understand where the flow is coming from.
Yeah, I've used that on external buses, but don't tend to for functional.
Yeah, well, see, my assumption is that eventually I'm going to have to do a gate sim.
Okay.
And if you got to do a gate sim, you got to put the timing in sometime. And I don't want to write a test and then later come back and rewrite it, because when I added timing in it, it shifted it enough that it's no longer getting the same results. And I hate that. I get
Two problems then.
bored real quick. So
Do it once, do it right.
the first time I do it, it's gotta be right, or pretty darn close to right, otherwise I just.
Just
Yeah, okay. You mentioned that Xilinx simulators don't work yet.
Yes,
Soon.
yeah,
And you also
we're
mentioned
hoping.
that GHDL doesn't.
Do external names yet, so you can't do the virtual transaction.
Okay, so you can do it provided that you.
Everything else you do, and
Okay.
what you have to do with GHDL then is fake external names. And the way you do that, and this is something you could do with VHDL 87 even, is instead of putting the signal inside the verification component, you'd have to put it in the package. Okay. And then anything that references the package gets access to it. But that means one type of that verification component per system, where you've got to have an array of them or something crazy like that. And then if you have an array of them,
short all your verification components together inadvertently, yes, okay.
yeah, and or you assign arbitrary indices to things, and you define a maximum in the library, and as soon as you start putting things like maximum in the library, to me, it's not a library anymore. It's something that each different person in the community could have a different setting, and that would frustrate me.
None from
No questions online? How many do we have online?
It's gone down from 15 to 12.
Okay. Cool. All right. Thanks everyone for coming. I do answer email, so if you end up using it. I answer email even from people who haven't taken our training. So, yeah, I appreciate if you find an issue that you do post an issue report on GitHub, or send me an email if you can't go to GitHub. I know I understand some. Well, there's some industries that don't let their folks go to GitHub. You know, it's a security thing. I can understand.
excellent indeed. Just.
Thank you.